So coming off of electricity, magnetism is a section that ties along with it very well. If you take a course in college, most likely a or a electricity course, it's going to be connected with the magnetism. Kind of short, E&M is the electricity and magnetism. So there's so many parallels, there's many connections, and they're really intertwined, and that's where we're moving to now. So magnets cause a space to be modified in the vicinity, forming a magnetic field. And the poles of a magnet are kind of analogous to electric poles or charges, but magnetic fields are separate from electric fields. They're two different kinds of fields. And the North Pole is where the field leaves, the South Pole is where they enter. And one of the key things with magnetic fields is that they are continuous loop. There's no beginning and end. Whereas you have an electric field, let's say I have a positive charge and negative charge, you know, the field starts here and then it ends here, and then it starts here and it ends here, and starts here and ends here. It's not true with a magnet. Magnet is a continuous loop. And so if you've ever done the iron filing lab, this is kind of fun. You know, you sprinkle iron filings on top of glass, and they separate out. And so in our lab, you were able to draw this out, you know, using the compasses and drawing. And so it's helpful to be able to see that. Let's say this is our North Pole, this is our South Pole. We have our field that passes through the middle, coming out of the North Pole and then down into the South Pole. And if you notice here, it's a continuous loop, right? It goes up and around and then through. And that's what we have with magnetic fields. Michael Faraday was one of the most important physicists, you know, really of all time, but especially in electricity and magnetism. He was born and did his study, you know, after the discovery of the battery, and he was able to do all sorts of experiments. This is some of his notes, you know, and some of his drawings. This is from his, you know, his writing, and visualizations are huge. You know, they actually started making visualizations of these magnetic fields and drew them, and this actually paved the way for drawing electric fields and then even gravitational fields. And so, you know, we've already studied electric fields, but the visualization part started actually with magnetic fields. So, you know, we've got our field passing right through the middle of the magnet, up out of the north into the South Pole. One of the really interesting things about this is, you know, in the Earth's core, we have our molten core that's, you know, moving around, and we have our magnetic field, and our magnetic field's actually essential for life. If we didn't have our magnetic field surrounding us, the Earth's radiation would, you know, destroy life on Earth. And so this is a critical part of our life on Earth, having the magnetic fields. So our compass seeks, if you notice, you know, in that lab, the compass itself actually points to the South Pole. So what's a little bit weird is the fact that if you look in the Earth, the northern part of the Earth actually is the southern part of a magnet, of the magnetic field, and then the bottom part of the Earth is north. And so when you have your compass, the compass is actually pointing towards the south side of Earth's magnet, which we call the North Pole. So that's a little counterintuitive there. And so compasses, you know, are themselves magnets, and they're easy to rotate. Some are in fluids, some are just in air. The ones we used in class were just suspended in air. If you look at the picture of the aircraft in the back of our room, that compass in there is filled with white propane. Yeah, as you know, it's just floating around. And so the compass points towards Earth's North's magnetic pole. But again, what's crazy is that it is the south side of Earth's magnet. And so even though we call it the North Pole, it's the south side of the Earth's core magnet. Okay, so one of the key things that we want to talk about as well is that there's no such thing as a monopole, because a magnet itself, when you split a magnet, because that field, you know, continues on through, you know, you could break it up, and then you could have a North Pole and a South Pole. In this case here, we've got, a large magnet. If we split that in half, what happens is this portion is now just considered north, and this portion is considered south. We could keep splitting them really all until microscopic size, and you're going to have a north side and a south side. That's because, there's certain objects that are called ferromagnetic that can be made into strong magnets and can stay in that form. And so when a material is unmagnetized, the domains are randomly oriented. But if you can get them to line up and you get the spin of the electrons, we've got our nucleus here, and then we have our electrons, and those electrons are spinning one way or the other, and the spin can be changed. And if you can get the spin all to line up with a bunch of sets of atoms, you can get a permanent magnet. Now, if you take that magnet and you start, hitting it against the floor or just dropping it, or just over time, those domains are going to start to switch and flip and become unmagnetized eventually. But you can remagnetize it. You can set it up. We have a device in our classroom actually that'll do that, and reset those the spin so that the magnetic fields are set up in the same direction. One of the cool things we like to do as well is you take a paper clip, and that paper clip has randomized domains, sets of atoms that are the spin is all kind of in all sorts of directions, and you could place that paper clip on top of the magnet, and those domains will flip and switch, and then eventually can be lined up and act just like a normal